So good morning everyone. Today's class refrigeration and air conditioning class number 36. Today we are going to study about a problem. In this problem, a two-stage refrigeration system which operates with a refrigerant ammonia flowing at the rate of 15 kg per minute through the evaporator, and the saturation temperature in the condenser and the evaporator units have been noted to be 40 degree and minus 15 degree centigrade respectively. So if the system has an intercooling by liquid refrigerant at 4.25 bar, determine the capacity and COP of the system. How these parameters would be affected if the compression is carried out in a single stage unit and the operating temperature limits are remaining same. Okay, using the pH chart and property tables and saturated ammonia refrigerant. So from the property table we can get the pressure of the condenser, which is corresponding to 40 degree. You can get the 15.457 bar actually. Okay, now you can see that there is a pressure of evaporator pressure which is corresponding to minus 15 degree centigrade, which is 2.37 bar, and the intermediate pressure is also given, which is 4.25 bar is given in the question. Actually you can see that the intermediate pressure, okay, intermediate pressure, the intermediate cooling by the liquid refrigerant at a 4.25 bar. From this we can get the intermediate pressure also. Okay, right. So all these things we get from this property table. Okay, now here the question is when we analyzing the question, we can see that when there is a two-stage refrigeration system, okay, there is a two-stage refrigeration system, it means that the compressor is actually two numbers of the compressor they are using, which is having a compression, that is there is an intermediate compression is also happening in there. Okay, so that is the first compression, it will compress up to around the evaporator pressure is around 2.37 bar, and after that it is again compressed into 15.57 bar. Up to that much we are going to compress it actually. Okay, right. Now we have to find this temperature, operating temperature limits, if the temperature limits are same, and how this is affected with respect to a single one. If there is a single one is there, and if this two-stage compressor is there, then how we can get the in the cases of the COP how it is differentiated. That is going that is here we have to answer. Okay, right. Now you can see that here we draw a pH chart given in the for this refrigerant. So you can see that here it is a pressure enthalpy chart. In this chart you can see that the pressure, the given pressure is pressure of evaporator, pressure of intermediate pressure, and the pressure of the compressor. Here you can see that corresponding pressures are given. Here you can see the corresponding pressures are given, and there will be a pH diagram we are going to draw. Okay, so the first point starting, it is in the here actually in the dry case. Okay, so here the first point started, and again you can see that there is a quantity of M1 which is flowing through this first compressor, and afterwards it reaches to the second point, and again it reaches to third point actually. Okay, so then the pressure is decreases, that means the pressure is same actually, but the enthalpy is decreases, and it reaches to the point 3, and again it is again the mass flow rate M2 which is flowing through this 3 to 4. That the second compressor, it is passed through the 3 to 4, and again it is get compressed, and this pressure is there actually 15.57 bar, which is passing through this condenser, and reaches to fifth stage, and from the fifth stage it reaches to the expansion device we are using, and from 5 to 6 it reaches to 5 to 6 actually. Now you can see that here the values corresponding to the H1, H2, H3 and H4 and H5 and H66, all these value you can collect it from the pH chart actually. Okay, if you look into this pressure, and there will be the dome is available, this dome is available in the refrigerant, and you are pointing, the first point is you are pointing the corresponding pressure P2 here, then the state point 1 is there, and corresponding enthalpy value from the bottom you can get the enthalpy value here. Okay, and when you draw a constant entropy line here, you can draw, if the constant entropy line is that there you can see that in here constant entropy line, and if you draw a constant and a straight line to the constant entropy line corresponding this pressure, and when it reaches into this intermediate pressure, that is a point 2 actually. You mark it as a point 2, and corresponding enthalpy you can collect it from the bottom. Okay, now again if you and then you come back to this dome point, and you reaches the point 3, and at the constant entropy line you draw a line and it reaches to 4, and corresponding for H4 you can collect it from the bottom, and it reaches to 5, and if you draw a straight line you can collect it from H5 and H6, both are same. From the bottom you can get the enthalpy of the H5 and H6. So all these value you can get it from this pH chart and also the table actually. Okay, now you got it all these values, but you can see that here H1, H3 and H5 all are checked and compared with the values that are given in the saturated property table. Now it is given that there is a mass flow rate of the M1 which is 15 kilogram per minute, which is passing through the evaporator. Okay, now you have to calculate the mass M2. So M2, how you are going to calculate is M2, which is the mass flow rate through the pressure compressor or the condenser. So you have the formula when the intermediate pressure or this intercooler is present. You know the formula actually, M2 which is equal to M1 into H2 minus H5 divided by H3 minus H5. Applying this formula you can get when you are putting these values actually, that is M1 is 15 and H2 and H3 H5 values, you put it here, you will get the value of the M2. So you have to study about this formula earlier. Okay, right. Now you know that the refrigerating effect which is M1 which is equal to H1 minus H6 actually. So you will get 15 into 1442 minus 390, which is the values of the H1 and H6, and you will get the value of these 15,780 kilojoule per minute. That is a refrigerating effect actually. Okay, now here you will get the capacity of the refrigeration system. How this capacity, that is for a 1 ton of the refrigeration, it is around 210 of the kilojoule per minute. So remember, 1 ton of refrigeration. Okay, I will write it in here actually. Yeah, 1 minute. Yeah, so 1 ton of refrigeration which is equal to 210 of the kilojoule per minute actually. Okay, 1 ton is which is equal to 210 kilojoule per minute actually. Okay, right. Now now you can see that here this value, that is 15780, is the total refrigerating effect. You got it from this this calculation, and that divided by 210, then you will get the tonnage. In tonnage, the refrigeration system. Okay, 75.14 is the tonnage. And now the work input into the driving both the compressors. Okay, see here you can see that there is a 2 compressors are there actually. That is the M1 passes through in a first compressor, M2 quantities passes through the second compressor. So M1, you can see that the M1 into H2 minus H1 will be the work input for the compressor 1, and M2 into H4 minus H3, which gives the work input for the compressor second actually. Okay, so you know the values of the M1 and M2, and you put the values of the H1, H2 and H3 and H4, and when combined the total work input, you can get this numerical value 1254.36 kilojoule per minute actually. Okay, now the coefficient of the performance, you know that the total refrigerant effect divided by work input. So you are getting here total refrigerating effect divided by work input, that is 15780 divided by 1254.36, that gives the 12.58. So that is the total work, that is the COP of the system. Okay, when you are using the 2 compressors, the two cylinder compressors, you can get that is here you can get the COP of this 12.58. okay, when you are using suppose a single stage compression, so that is a second 2-stage compression you used in the previous case, but in here you are using a single stage compression. So you can see that in the figure that is the refrigerant flows the path of the 1 2 dash actually. If you look into that pH chart, you can see that the 1 to 2 dash is the actually the compression actually. So there will be a single compression is happening, and you know that the mass flow rate is the earlier mass flow rate 15 kilogram per minute is used. Okay, and you can see that the from the pH chart you will get 1528 kilojoule per minute is the total refrigerating effect. So refrigerating effect will not be changed actually. So 15780 kilojoule per minute is the total refrigerating effect, which is we already get it by the calculation from in the previous section, and the capacity is actually you will get when 75.14 ton actually. Okay, but the only difference is here you can get the difference in the compressor unit actually. Okay, the work input to the driving the compressor unit is changed. So the COP is only changing. Okay, so there will be the only one is thing is changes is the COP actually. Okay, if the compressor, if you are using there will be the total work input to the compressor will change. Okay, so that is why we can change the in the COP, but there is no change in the refrigerating effect. Okay, whether you are using the single stage or the double stage, there is no effect difference in the refrigerating effect, but the only difference will be in the COP of the system and the total work input to the driving the compressor. Okay, now here you can see that the total work input here it is the single M into H2 dash minus H1. So M is the first one, that is 15 kilogram per minute, and you can put the values of the enthalpy values and you will get a work input, it is 1290 kilojoule per minute. So that gives that the COP of the total system will gives 12.23. So from these two examples, that is the single stage and the multi-stage, you can clarify that the work input that is the work required, which is reduced from this 1290 kilojoule per minute to the 1254.36. So what is the exactly the difference is that the work requirement we can reduce whether if you are using a multi-stage actually. Okay, so in the earlier case you can see that it is 1290 is for the single stage. അതായത് നിങ്ങൾ സിംഗിൾ സ്റ്റേജ് കംപ്രസർ യൂസ് ചെയ്യുകയാണെങ്കിൽ 1290 ആയിരിക്കും നിങ്ങളുടെ ടോട്ടൽ വർക്ക് ഇൻപുട്ട് എന്ന് പറയുന്നത്. പക്ഷേ നേരെ മറിച്ച് നിങ്ങളൊരു മൾട്ടി സ്റ്റേജ് യൂസ് ചെയ്യുകയാണെങ്കിൽ ടോട്ടൽ വർക്ക് ഇൻപുട്ട് എന്ന് പറയുന്നത് 1254 ആയിരിക്കും നിങ്ങളുടെ ടോട്ടൽ വർക്ക് ഇൻപുട്ട് എന്ന് പറയുന്നത് ആക്ച്വലി. ഓക്കെ, ഇഫ് യു ആർ യൂസിങ് എ മൾട്ടി സ്റ്റേജ് ഓർ ദ ഡബിൾ സ്റ്റേജ്. ആൻഡ് COPൻ്റെ കേസിൽ അതുപോലെ തന്നെ COPൻ്റെ കേസിൽ ഇറ്റ് ഈസ് ഇൻക്രീസ്, ദാറ്റ് ഈസ് 12.23 ആയിരിക്കും നിങ്ങൾ സിംഗിൾ സ്റ്റേജ് യൂസ് ചെയ്യുകയാണെങ്കിൽ. പക്ഷേ മൾട്ടി സ്റ്റേജ് യൂസ് ചെയ്യുകയാണെങ്കിൽ 12.58 ആയിരിക്കും, അതായത് കൂടുതലായിരിക്കും. ഓക്കെ, COPയും കൂടുതലായിരിക്കും നിങ്ങൾക്ക്. Okay, so this is all about this is the first problem, and I think the next problem you can move it to next problem. In this problem you can see that a 30 ton of the refrigerating plant which is using the ammonia as a refrigerant to operate in a two-stage vapor compression refrigeration system which having a direct contact heat exchanger. So you can see that there is a heat exchanger is included in the system, and it is using a two-stage vapor compression system, and its plant is using the ammonia as a refrigerant, and its tonnage is 30 ton. Okay, from this statement you can get this much values, this much information, and the system has a considering the temperature of 40 degree. Okay, so the condensing temperature is 40 degree, evaporating temperature is minus 30 degree, and the saturation vapor which is enters the both compressor and saturated liquid enter the expansion valve. So the considering these two stages of the compression, you can see that this compression will be the isentropic, and the minimum work input to the drive of the compressor and the coefficient of the performance of the system you have to find. Okay, and they are also asking that if the compression process is done in a single stage, okay, how these parameters would get affected if the compression process is done in a single stage. So you have to compare that whether if you are using a single stage compression process, and what will be the changes in the COP and also the work input, all these things, what will be the change. Okay, now you are using this two-stage vapor compression system, but if you are using a single stage, then what will be the difference in the values of the power and also this work input and all this COP, etc. Okay, now in this question you can use the pH chart and also you see that the pressure actually. Okay, so you can see the from the table you can also get the pressure actually, pressure corresponding to these temperatures you will get. Okay, now here your one thing is missing, that is the intermediate pressure actually. See here you can see that two pressures you can see, but the only thing is there is a no intermediate pressure is not given, because it is a two-stage compression system. You have to provide a intermediate pressure system. Okay, so for the intermediate pressure system there is a formula which is given in here. You can see that PI, which is equal to root of PC into PE. So if you have the two pressures, you can simply multiply with these two pressure and giving a root, you will get the intermediate pressure. So as per this calculation, you will get 430 kilopascal as the intermediate pressure. Now you will get the various values of the H1, H2, H3, H4 and H5 and H6. And also here also one more term is coming in this H7 and H8 also is coming. So all these you will get from the pH diagram. Okay, so we can see about this pH diagram, how this pH diagram is there actually. So now we can see the schematic diagram also. Okay, so the section is there is a two stage compression actually. So one is a low stage and another one is a high stage, and there will be a heat exchanger is connected in between these two systems. Okay, so first from the starting the evaporator is there. From the evaporator you can see that the stage point 1 is going to the refrigerant is flowing to the lower pressure compressor, and from the lower pressure it get pressure, and then that pressurized refrigerant which is passed through this direct contact heat exchanger, and it get heat exchanged, and then what happens? So it becomes that amount of this refrigerant which is passing through an expansion device 7 to 8 and reaches to the evaporator. But you can see that here after this one there will be that refrigerant will be coming to the high pressure compressor actually, and it again pressurized, and then it going to this condenser tube actually. So from there it get condensed and it becomes liquid actually. Okay, that liquid almost 90% of that liquid, and again that 10% of that when this 90% of liquid and that gases mixture of this refrigerant is passing through the expansion valve, and what happens, it goes when the expansion valve is there, almost that gases stages will be also there, and it comes to again the direct contact heat exchanger. Okay, right. Now you can see here the pH chart of this the entire system actually. So here you can see when you are using a two-stage system and a single-stage system, both pH chart are given here actually. So in the two-stage pressure system, you can see that 1, 2 and 3 and 3 to 4 and 4 to 5 and 5 to 6. So up to this 5 you will understand, that is because two compressors are there. So up to this system you understand, that is starting from 1, 2, 3, 4 and 5 up to the 5 you can understand. But what happens here and 6, 7, 8 actually. So here you can added this heat exchanger. That is the reason here you can see that there is a 5, 6, 7, 8. So 6, 7, 8, all these things are coming because of this heat exchanger. Okay, so you can see when 5 to 6, you can see here the 5 to 6 it reaches here expansion device. In between there is an expansion device. After that it reaches to 6 and it is passing through this heat exchanger. It get cooled and reaches here as a 7. Okay, it reaches as a 7. So 5 to 6 it reaches here, and 6 to 7 heat exchange is happening here, and from the 7 to 8, so 7 to 8 another expansion valve you are placed here, and what happens? So it gets expanded and it is passing through this evaporator actually. Okay, so after this 7 to 8 expansion device, and then 8 to 1 it reaches here actually. So this is all about this pressure enthalpy diagram of this this problem actually. Okay, now when you are coming to the picture of the single stage, that is 1 to 2, 2 to 3 and 3 to 4. Okay, a single stage. Now again we are going to back our this analytical thing, that is here you can see that when the pH diagram, if you are taking the pH diagram, if you draw that drawing, and you will clearly get the H1, H2, H3, H4, H5 and H6 and H7 and H8 values corresponding pH chart actually. Okay, now you can see that if the 1 ton of the refrigeration which is equivalent to the heat absorption rate, then the mass M1 is passing through, which is equal to 3.5 Q divided by H1 minus H8. So that is H1 minus H8 is the refrigerating effect, and you can see that is H1 is here and H8 is also here. When you put in these numericals in here, you can get the M1's value. Okay, now you can see the energy balance equation, because you are using a heat exchanger, so that is why you can use the energy balance equation, and M1 M2, that is M1 into H2 plus M2 into H6, which is equal to N2 H3 plus M1 H7. How this equation is happening? Okay, so you can see here, you can see that here in this diagram it is refrigerant is circulating M1, and here in this part it is M2 is the refrigerant which is circulating here actually. Okay, so 5 to 6 and 6 to M2 into 6 H6, which is coming to the heat exchanger, and also this 2, that is M1 into 2 is also coming to this heat exchanger, but H7 into M1, which is going to from the heat, is going from this heat exchanger, and that is a refrigerant is going from this heat exchanger, and 3, that is H3 and this M2. Okay, M2 and H3, which is the going. So going, all goings are added into one side and all comings are added into another side. That is here actually. So M1 into H2 plus M2 into H6, which is equal to M1 into H3 plus M1 into H7. Okay. Now mass of the refrigerant passing through this condenser actually. So you can see from the condenser formula you can get that is M2, which is equal to M1 into H2 minus H7 divided by this H3 minus H6. You will get the numericals, and if you you can see that 0.1115 kilogram per second is the M2 mass. So M1 and M2 masses you will get it. That is a mass flow rate actually. Okay, not only the mass, it is a mass flow rate actually. Per second it is a rate. It means that per second this much kilogram is passing through the entire system actually. Okay, now you can see the total work of the compression actually. Okay, because it is a 2-stage, you can see that the first part and second part. Okay, so the first part the mass flow rate is M1, and the second part the mass flow rate is M2. So from this equation you can see that M1 into H2 minus H1 plus M2 into H4 minus H3, and when you are applying these numericals, you will get a value of 35.33 kilowatt. Okay, that is the total work of the compression actually in this 2-stage case. Okay, and the corresponding COP, you can see that the refrigerating effect divided by the work input. See here you can see that there is a 30 into 3.5. What is mean by the 3.5? 3.5 is 1 ton, which is equal to 3.5 kilowatt actually. Okay, so here it is given as a 30 ton. So 30 into 3.5, that is that much value of the kilowatt actually, divided by work input is also is kilowatt. So that is why 35.33, and you will get the COP of the 2.97 actually. Okay, right. Now you can see that in the second section. So in the second section it is a single stage compression is carried out. Okay, so H1, which is equal to 1405 kilojoule per kilogram, and H2, which is equal to 1805 kilojoule per kilogram. So that is a H3 equal to H4, which is equal to 372 kilogram per second, kilojoule per kilogram. Okay, so when in the single stage, the H1 enthalpy values are different, and you will collect the enthalpy values, and mass flow rate, you have to find the mass flow rate of the single. So M is equal to 3.5 Q divided by H1 minus H4, which is equal to 0.0979 kilogram per second, which is the mass flow rate. Okay, the entire mass flow rate, because here it is a single stage compression. Now what is the work input actually? So work input is equal to that single stage in the mass M into, that is 0.0979, that is into H2 minus H1. You will get a value of in kilowatt 39.19. and the coefficient you will got it after submitting these values, you will get it 2.68. See here, you can see that it is 2.68 only when you are using the single stage, but when you are using the multi-stage, you can see that 2.972. okay, right. So the percentage of the increase in the compression work for the single stage is which is equal to, that is when you are giving some percentage value, you can collect that value, that is the percentage increase in the compression. Okay, so when the single stage compression, if you are using a single stage compression, you can see that 39.16 which is the value of the total work input minus 35.33 is the total work input by using the multi-stage actually. So you will get a 10.84 percentage of the increase in the compression work is happens. And similarly in the COP case, you can see that the 10.89 percentage of the increase in the COP actually. Okay, I hope you got it all this problem. Okay, in the next class we can study about the simple vapor absorption refrigeration system. Okay, so today's I think this is enough for you. Okay, anyway, thank you.